Hi, I'm Storm Racer. In this video, I will give a full answer to the question, how many patterns can you make on a Rubik's Cube and why? Let's get started. If you have read or watched anything about the mathematics of the Rubik's Cube, you'll probably know the total number of patterns on a Rubik's Cube to be this pretty big number. That's about 4.33 times 10 to the 19th power. And if your source gives any explanation for this, you've probably also seen this formula. Okay, the top bit is easy to explain with simple combinatorics. It is the total number of different ways you can assemble your cube if you take it apart. But what about the bottom bit? It turns out that not every assembly is solvable. Due to certain constraints on how you can move the pieces, if you assemble your cube randomly, there's only a 1 in 12 chance that the assembled pattern is solvable. So, to obtain the number of patterns you can make using only legal moves, you need to divide by 12. But where does this 12 come from? That will be our focus for today. But before that, let's quickly review the top bit first. Now I have disassembled the cube. The first thing you notice is that all the center pieces are attached to the core. So, although they can still rotate, their positions relative to each other are fixed. Two patterns that are merely oriented differently count as the same pattern. In addition, there is no picture on this cube, so the 4 different ways each centerpiece might be facing are visually indistinguishable. Well, very often you will have a logo on one of the centerpieces like this one, but since we don't really care about it when determining whether we have solved the cube or not, it doesn't matter, and we might as well pretend that it does not exist. So there is really only one possible configuration for the centerpieces, and they don't add anything to our calculation. Or rather, they don't multiply anything. Now let's assemble the other pieces. There are a total of 12 edge pieces and 8 corner pieces. You have 12 pieces to choose from for your first edge position. Then for the next edge position, you have 11, then 10, and so on. So the total number of combinations of edge positions is 12 times 11 times 10 all the way down to 1, which is 12 factorial. For each edge piece, there are 2 possible orientations. You make the choice for each of 12 edge pieces independently. So the total number of combinations of edge orientations is 2 to the 12th power. Likewise, for corner pieces, the total number of combinations of corner positions is 8 times 7 times 6 all the way down to 1, which is 8 factorial. And each corner piece has 3 possible orientations, so the total number of combinations of corner orientations is 3 to the 8th power. Multiply everything together, you get the total number of possible ways to assemble your cube. 12 factorial times 2 to the 12th power times 8 factorial times 3 to the 8th power. Now for the division by 12 part. If you know any method for solving a Rubik's Cube, take a look at it. For example, here I have one possible set of algorithms for the CFOP method. In the OLL step, there is no algorithm for flipping a single edge piece or for rotating a single corner piece. In the PLL step, there is no algorithm for swapping a single pair of pieces. Why? Because these situations never happen. If your cube has been scrambled legally, you will never need to flip a single edge, rotate a single corner, or swap only one pair of pieces to solve it. And these are exactly the 3 conditions for a pattern to be solvable: piece permutation parity, number of edge flips, and number of corner rotations. From here on, I will use state interchangeably with pattern. We'll talk about permutation first. If you are already familiar with the parity of a permutation, you can skip to the next section. A sequential move puzzle is all about rearranging things, and there is a mathematical tool for it: permutation. A permutation is a record of how things exchange their positions. To present a permutation, you write down a list of items in one line, and reorder them in the second line to indicate that the item at the top should go to the corresponding item at the bottom. The precise meaning of these items depends on your application. For our purpose, the items represent all possible positions for the edge and corner pieces, and you take whatever piece that is at the top position and move it to the bottom position. Each move can be represented by a permutation. For example, I orient my cube so white is up and blue is right. If I rotate the white face 90 degrees clockwise, or U in the standard notation, then the pieces that were in the 4 top layer corners cycle their positions one place clockwise. Similarly for the edges, the bottom 2 layers are left unchanged. Likewise, if I rotate the blue face 90 degrees clockwise, or R in the standard notation, this is what I get. Keep in mind that these items are positions, not pieces. You don't take the piece indicated by the item and move it. You take whatever piece that is located at the position indicated by the item and move it. When one move follows another, their permutations are composed. We're dealing with Rubik's cubes, and in the standard Rubik's cube notation, a sequence of moves is executed from left to right. So, we use the same convention for the composition of permutations. Pay attention to this if you are already familiar with permutations but use the opposite convention. To compose 2 permutations, put the first permutation on top and the second permutation below it. For each item, see where it goes in the first permutation, and you get another item. Look up this item in the second permutation and see where it goes. This is where your original item should go in the composed permutation. We have calculated the permutation for the move sequence UR. Let's check. We rotate the up face, then the right face. And yes, the actual movement of the pieces do match the composed permutation. You might have noticed that the white, orange, blue corner has been rotated, but this is not reflected in the permutation. That's not a problem. It is possible to extend the representation to include orientation in the permutation, but for our purpose, position is all we care about, so this is good enough. This also tells us that you can indeed represent any state using permutation by just recording where every piece is, and a sequence of moves that has the same permutation will bring you from the solved state to this state. Take this one for example. There should be a white, blue, red corner piece. Where does it go? It goes to the place of the yellow, blue, orange corner. And there should be a white, orange, blue corner piece. Where does it go? It goes to the place of the white, red, green corner. Similarly for every other piece. The following discussion applies to permutations in general, so we will write numbers instead of drawing pieces. In our proof, the value of the numbers do matter. You can give numbers to your items by ordering them arbitrarily. Now that we have assigned numbers to the items, we can define the parity of a permutation. We assume that the first line is ordered from smallest to largest and look at the second line. The second line is the new order of the numbers after they have been rearranged. If a larger number goes before a smaller number, then it differs from their original order. Each such instance is called an inversion. The parity of the total number of inversions is called the parity of the permutation. For example, this permutation has 23 inversions, and so is an odd permutation. A permutation can also be represented more concisely using the cycle notation. A cycle is a list of items in parentheses, where the first item goes to the place of the second item goes to the place of the third item, and so on. And it loops back, so the last item goes to the place of the first item. You write a permutation by using as many disjoint cycles as needed. For example, in this permutation, 1 goes to 5, 5 goes to 8, 8 goes back to 1. So you have a cycle 158. Then 2 goes to 9, 9 goes to 4, 4 goes to 6, 6 goes back to 2. So you have another cycle 2946. The remaining numbers 3 and 7 don't move. You can write each one in its own cycle, or more commonly, just omit them. So this permutation can be written as 158, 2946. When two intersecting cycles meet each other, they're composed according to the rule of permutation composition. A cycle can be decomposed into transpositions. A transposition is a permutation that swaps two items, or a cycle of length 2. One benefit of cycle notation is that this decomposition is quite clear. You exchange the first item in the cycle with all following items one by one. For example, the cycle 2946 can be decomposed as 29, 24, 26. A transposition can be further decomposed into adjacent transpositions. An adjacent transposition is a transposition that swaps two numbers that differ by 1. To do so, you start by swapping the smaller number with the next one up. Go all the way until you reach the larger number, then go back down. For example, the cycle 26 can be decomposed as 23, 34, 45, 56, 45, 34, 23. An important property of adjacent transposition is that if you compose it after any permutation, it always changes its parity. Start from where the first permutation ends. Since an adjacent transposition swaps two numbers that differ by 1, there is no other number whose value is between them. So, any number that is larger than one of them must also be larger than the other, and any number that is smaller than one of them must also be smaller than the other. So, an inversion containing none of them, or only one of them, before the swap, will still be an inversion after the swap, and vice versa. The only possible change is the inversion between the two numbers. If the smaller one is in front before the swap, then the swap creates one inversion. If the larger one is in front before the swap, then the swap removes one inversion. In any case, the parity of permutation changes. Now we can decompose any permutation into adjacent transpositions. Since each additional adjacent transposition always changes the parity of the number of adjacent transpositions is the same as the parity of the permutation. Note that parity is a property of a permutation, not one of its decompositions. So it doesn't matter how one decomposes a permutation. This also implies that you can only ever decompose an even permutation into an even number of adjacent transpositions, and an odd permutation into an odd number of adjacent transpositions. To compose two permutations, we can always decompose both into adjacent transpositions first. The new permutation will have the same parity as the total number of adjacent transpositions from the two permutations. This shows that, in terms of parity, composing two permutations behaves exactly like adding two numbers. Composing two permutations of the same parity will give you an even permutation, and composing two permutations of the opposite parity will give you an odd permutation. A transposition between two numbers that differ by n can be decomposed into 2n-1 adjacent transpositions, so it is always an odd permutation. A cycle of length n can be decomposed into n-1 transpositions, so its parity is the same as n-1. To find the parity of a permutation from its cycles, take the length of each cycle, subtract 1 from each, and add them together. The parity of the permutation is the parity of the sum. After this lengthy discussion of the parity of a permutation, we are finally ready to apply it to the Rubik's Cube. Every 90-degree turn produces a 4-cycle of edges and a 4-cycle of corners. 4 minus 1 plus 4 minus 1 is 6, an even number. So each move of the Rubik's Cube is an even permutation. Thus, a solvable state must be an even permutation. A random permutation has an equal chance of being even or odd, so there is a half chance that a randomly assembled cube will have an even permutation. Now let's move on to edge flip and corner rotation. Here you can see that I have put some markers on the cube. Specifically, on each edge piece and each corner piece, I've chosen one facelet arbitrarily to put a marker on. Make a copy of this for reference. Then I scramble the cube. Now, compare the markers on both cubes at each position. Each corner piece can be rotated in steps of 120 degrees, and we will count how many steps they have rotated clockwise relative to the reference markers. We will also count how many edges have flipped. Corners first. This corner is not rotated. This is rotated 2 steps. 1 step. 1 step. Not rotated. 1 step. Not rotated. 1 step. And then the edges. This is not flipped. This is flipped. Not flipped. Not flipped. 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 Not flipped. Not flipped. 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 Not flipped. That's a total of 6 rotations and 6 flips. I'll do it a few more times and see what we can discover. What can you discover from these numbers? Well, you'll see a lot of 6s. It is true that the rotation number has a 36% chance of being exactly 6, and the flip number has a 45% chance. But other numbers do occur. You might be guessing that the rotation number is always a multiple of 3, and the flip number is always an even number. And you'll be correct. This is true for any arrangement of markers, but for our purpose, it suffices to prove it for one particular arrangement, and I'll choose one that is highly symmetric and gives the simplest proof. In this arrangement of markers, I put the marker on the white or yellow facelet on any corner piece. And for edge pieces, I made it so that on every face, there is exactly one pair of opposite edges with markers. We will be using modular arithmetic. In modular arithmetic mod n, 2 numbers are the same if they give the same remainder when divided by n. So in mod 3, 3 is the same as 0, 4 is the same as 1, 5 is the same as 2, and so on. Now scramble the cube. We can see that from whatever state, since all corner markers are on the white face in the reference configuration, if you rotate the white face, the new reference marker of each corner piece is in the same direction as the old one, which means its rotation number doesn't change. The yellow face is the same due to symmetry. If you rotate blue face clockwise, then the piece that was in the white, blue, or red position will get a new reference marker that is rotated counterclockwise one step relative to the old one, so its rotation number increases by 1 mod 3. The same with the piece that was in the yellow, blue, orange position. On the other hand, the piece that was in the white, orange, blue position will get a new reference marker that is rotated clockwise one step relative to the old one, so its rotation number decreases by 1 mod 3. The same with the piece that was in the yellow, red, blue position. So the net total change of rotation number is 1 minus 1 plus 1 minus 1, which is 0 mod 3. The green, red, and orange faces are the same due to symmetry. Since any single move gives you a net rotation number of 0 mod 3, and the solved state has a rotation number of 0, all solvable states must have a rotation number of 0 mod 3. There is a 1/3 chance that a randomly assembled cube will have a rotation number of 0 mod 3. For edge flip, it's much simpler. I have arranged the markers such that in any move, all 4 affected edge pieces will get a new reference marker in the opposite direction to the old one. So they will all be flipped, and any single move gives a net flip number of 4 mod 2, which is 0. The solved state has a flip number of 0, so all solvable states must have a flip number of 0 mod 2. There is a half chance that a randomly assembled cube will have a flip number of 0 mod 2. So in total, the probability that a randomly assembled cube satisfied all 3 solvability conditions is 1/2 times 1/3 times 1/2 equals 1/12. We can now finally properly answer the question: how many different patterns can you make on a Rubik's Cube? And the answer is 43 quintillion, 252 quadrillion, 3 trillion, 274 billion, 489 million, and 856,000. Actually, there are 2 remaining issues. First, we need to show that all combinations of piece permutation parity, edge flip number mod 2, and corner rotation number mod 3 are equally likely. Second, we need to show that every state that meets these 3 conditions can indeed be solved. But these are mostly mechanical tests that don't provide much insight. So, although I've promised a foolproof, in the spirit of mathematics textbooks, these parts are left to the viewers as an exercise. Before we go, I also want to address a bonus question. Rubik's Cubes with pictures are often found as novelty items, like this one I made. How many patterns do these ones have? Well, it depends on the symmetry of the picture, but most often they don't have any symmetry. So, now the orientation of the center pieces are visually distinguishable. Each face has 4 possible orientations, for a total number of combinations of 4 to the 6th power. But notice that although each move produces an even permutation of pieces overall, it is a composition of an odd permutation of corners and an odd permutation of edges. At the same time, it also rotates one center piece by 90 degrees. So the parity of edge permutation, corner permutation, and number of 90-degree turns of the centers must be the same. And in a randomly assembled cube, there is a 50% chance that the parity of the centerpiece rotation does not match the edge and corner permutation. So, to get the total number of patterns you can make on a Rubik's Cube with non-symmetric pictures, multiply by 4 to the 6th power and divide by 2, and you get this. About 8.86 times 10 to the 22nd power. And that is the full answer to the question, how many patterns can you make on a Rubik's Cube? Thanks for watching.